This is part B for our unit on exploratory factor analysis. So now, at this point, we have created something that I called factor score A, and we went through a series of 6 steps with that factor score. And what I'm going to do next is create a new variable called factor score B, and we're going to go through all the exact same 6 steps all over again. We'll do the exact same thing with factor score B that we already did with factor score A. But there's going to be one important difference between factor score A and factor score B. Recall how we created factor score A. We devised a system of weights. We had each x variable was multiplied by a weight, and then we summed it up to get a score on factor score A. And then there was the question, how did we decide what these beta weights were? How did we select the beta weights that each x was multiplied by to get our factor score? We identified beta weights. There was a matrix algebra procedure that was used to identify beta weights that would produce a factor score that would explain the most possible variance that could be explained in all the variables. We identified a single factor score that explained as much as possible of the variance in the original x items. And that was how the weights were selected for that factor score. Now for factor score B, we're going to select a factor score. We want to identify a set of weights that will produce a factor score that will maximize the amount of variance it will explain, not in the original x variables, but in the residuals. So the key difference between factor score A and factor score B, factor score A is a score that's designed to explain as much as possible of the variance in the original x variables. Factor score B is a score that will be designed to explain as much as possible of the variance in the residuals. Those are the residuals we just created in the previous step. Let me back up to that slide to remind us what we're talking about. So here is the slide showing the residuals. This first column is everybody's score on x1 with factor score A extracted out of it. It's all the stuff that factor score A couldn't explain. Here's everyone's score on x2 with factor score A extracted out of it. It's all the stuff on item number 2 that couldn't be explained by the factor score. So here we have a table of everyone's residuals, or standardized residuals, on the 4 items from our questionnaire. So factor score B, we want to identify what are the beta weights that we can plug in here. So we take each x item and multiply it by beta weight, but we want to produce a factor score not that will explain as much variance as possible in our original x items, but that will explain as much variance as possible in those residuals, the leftovers, the stuff that couldn't be explained by factor score A. And as it turns out, when we do this, we will end up with a factor score B that has an exactly 0 correlation with factor score A. There will be no correlation between these two factors because factor score A explained all the variance it could in the original x items, and factor score B is based on the variance you could explain in the residuals. And the residuals is all the stuff that's not correlated with factor score A. So that means factor score B will have an exact 0 correlation with factor score A. So to summarize, we're using matrix algebra to create a factor score B. We'll use matrix algebra and calculate a set of beta weights, or weights, values are selected to maximize the portion of variance that can be explained in all the residual x variables, not the original x variables, but we're explaining variance in those residual x variables, and we want to figure out what weights will produce a factor score so that the factor score explains the maximum possible variance it can in those residual variables. Before I go on, let me make a quick note about terminology here. I just said that factor score A and factor score B will have a 0 correlation. Another way of saying the same thing is to say that these two factors will be orthogonal to each other. In statistics, if I say two variables are orthogonal, it means the same thing as saying they have an exactly zero correlation. Orthogonal means having a zero correlation. The word orthogonal comes from the root ortho, I believe, which means to be at right angles. So for example, if you go to the orthodontist, that is a person who puts your teeth at right angles to each other. And in statistics, we can represent a zero correlation between two variables by drawing two lines at right angles. So if I have one line represents one variable and another line represents another one, if I draw them at right angles, that would be depicting a zero correlation, meaning as you go up and down on this variable, it doesn't make a difference for if you go up and down on that one. If I go up and down on this one, it doesn't make a difference for where I am on the first variable. In contrast, if I drew what I would call an oblique relationship, here I have two lines that are not at right angles, so if I'm going up and down on this one, I'm also to some degree going up and down on the other. Or if I draw two lines right on top of each other, that would be a perfect positive correlation. So we can represent the strength of a correlation by drawing two lines, and if the two lines are at right angles to each other, that would be the way we would depict a zero correlation. And so that is why a zero correlation is often called an orthogonal relationship in statistics. And orthogonal is a word that's commonly used in doing factor analysis. And so I use the phrase here to say factor score B and factor score A will be orthogonal, and it's just another way of saying their correlation will be zero. So here are what things look like up to this point in our current example. So we started off by creating factor score A, and each x variable was multiplied by a weight to create factor score A, and our weights for x1, we had 0.79 for x1, negative 0.42 for x2, negative 0.6 for x3, 0.78 for x4. So those were the weights we used to create factor score A. And now we're going to create factor score B, and the weights that we get when we calculate a factor score B, the weights we get that will maximize the extent to which factor score B explains variance in those residuals, the residuals of x. The weights we get are a weight of 0.47 for x1, 0.76 for x2, 0.52 for x3, and 0.34 for x4. So to create factor score B, I will take x1 times 0.47, x2 times 0.76, x3 times 0.52, x4 times 0.34, and I will get a score for factor score B. And in our example now, at this point, everyone in our sample has a score for factor score A, and now everyone has another factor score B, their score on factor score B. So everyone has a score on factor score A, and everyone has a score for factor score B. So if I take that data set and those two variables I created, factor score A and factor score B, and calculate the correlation, that correlation should be 0. And here I test that to see, and indeed that's how it comes out. So I just took that data set and I used SPSS to calculate the correlation between factor score A and factor score B, and as you can see, the correlation is exactly 0. And as our giraffe thinks up here, dig the orthogonality. Orthogonal is a word. I don't know if people ever say orthogonality, but that's what our giraffe is thinking. So this just shows that indeed, when I extract factor score B, and going back to our previous slide, recall that these weights we used for factor score B were ones that would maximize the extent to which factor score B would explain variance in the residuals, the leftovers, the stuff that couldn't be explained by factor score A. And when we do that, it produces a factor that has an exactly 0 correlation. In other words, it is perfectly orthogonal with factor score A. We have two orthogonal factors. And now we're going to take each of those steps that we did with factor score A, and we're going to do them all over again for factor score B. So recall, for factor score A, we created a pattern matrix. We had a series of regression equations, one equation for each item on our assessment instrument, and each item was predicted using factor score A. We used factor score A to predict each item on our assessment instrument, and the beta weights from those regression equations were our pattern matrix. Now we're going to do the same thing, but at this point we have scores on both factor score A and factor score B. So now we're going to do a multiple regression equation. Instead of predicting each item using only factor score A, we're now going to use both factor score A and factor score B to predict the item. So we have this one regression equation here where we say item 1 from our assessment instrument, x1, is predicted using both factor score A and factor score B. And our regression equation is predicted score for item 1 is equal to a slope times a person's score on factor score A plus a slope times that person's score on factor score B. And then we do the same thing for x2, the second item on our questionnaire. That item is predicted by a slope times a person's score on factor score A plus a slope times a person's score on factor score B. And the same thing for predicting item 3 and item 4. And however many items we have on our assessment instrument, again, we do one regression equation for each item in which we use both factor score A and factor score B to predict the score for that item. Now, one thing, whoops, one head wasn't ready to go there. Here we go. So one thing to note in these regression equations is that when we add factor score B to our equation, it will not change the slope for factor score A. This is something that's different from what usually happens in most regression, that if I have a simple regression with just one predictor and then go to multiple regression where I add a predictor, the beta weights change. That's because a beta weight in simple regression with just one predictor tells me how much that predictor explains variance in an outcome. If I have two predictors, it tells me the percent of variance that's explained in the outcome after controlling for the other predictor. The beta weight gives me the effect of one variable controlling for all the other variables in the equation. And the effect of a variable after controlling for all the other variables in the equation is different from the effect of that same variable without controlling for the other variables in the equation. That is, the effect controlling for the other variables is different from the effect not controlling for the other variables. So you would think that if we add factor score B, which means that this beta weight right here, this beta weight for A1, is the effect of factor score A predicting this item x1. So beta weight right here, beta weight A1, gives me the effect for factor score A predicting item x1 after controlling for factor score B. And you would think that the effect of factor score A on x1 after controlling for factor score B might be different than the effect without controlling for factor score B. But that's not the case. You get the exact same beta either way. Why is that? Can you think of why that is? Recall that factor score A and factor score B are orthogonal. They're uncorrelated. And what that means is because they're orthogonal, the effect of factor score A by itself or the effect of factor score A after controlling for factor score B is the same thing. It doesn't change after controlling for factor score B because factor score B has nothing whatsoever to do with factor score A. The correlation between these two factors is zero. So the effect of A by itself is the same as the effect of A controlling for B. So because the factors are uncorrelated, or if I use the more precise language, I should be saying because these components are uncorrelated, because I'm actually doing principal components analysis here, but because my components or factors are uncorrelated, it means the betas for factor score A will be unchanged after controlling for factor score B. Whatever betas I got in my first step when I had just factor score A by itself will be the same as the betas I get in this step when I have factor score A controlling for factor score B. It always comes out the same either way. And here is some output just to prove what I'm saying is true. So up at the top I have the results from a regression equation that I showed you previously when I used factor score A to predict x1, how much a person felt he or she was selfish. And in that analysis, we got a beta weight of 0.79. So now I run a regression where I use both factor score A and factor score B to predict x1. And the beta weight for factor score A is still exactly 0.79. It did not change. And my beta weight for factor score B is 0.47. And as we've seen before, 0.79 and 0.7, these beta weights are the same weights we used to create the factor scores in the first place. The weight we used to create factor score A for item x1, we multiplied x1 times 0.79 to create factor score A, and we multiplied x1 times 0.47 to create factor score B. So the weights we use to create our factors are the same thing as the beta weights we get when we use our factors to predict the items. And as we see here, our adding factor score B did not change the beta weight we got. We got 0.79, 0.79. We got the same beta weight in both cases. So now that we've added factor score B, we have a new pattern matrix. This is the pattern matrix we get when we run a series of regression equations using both factor score A and factor score B to predict each item on our assessment instrument. And so we have the loadings for how much each item loads on factor score A. These are the beta weights using factor score A to predict each item. And these are the exact same loadings we had in our previous step when we had only factor score A before we extracted factor score B. So again, because factor score A and factor score B are orthogonal, they're uncorrelated, these loadings for factor score A will not change after adding factor score B. And the new loadings we have here are for factor score B, how much each item loads on our second factor. Or again, maybe I should be calling these components rather than factors because we're doing principal components analysis. And if we look at these, we might notice, for example, it looks like variable x1, x3, and x4 all produce stronger loadings on A than they do on B. So we might say the factor score A might be a good representation of these three items, whereas x2 seems to have a stronger loading on factor score B, so maybe it's measuring something different, that maybe items 1, 3, and 4 are capturing factor score A best, and item x2 is capturing factor score B best. And this is the type of, I'm kind of doing a subjective analysis here to get a sense of what these items are doing, but this is the way that an exploratory factor analysis can be interpreted when you're looking at results like this. And as before, we will create a structure matrix, and the structure matrix will be the same thing as the pattern matrix. The only difference is how we go about creating it. So the pattern matrix was the matrix of beta weights when we use the factor score to predict each item, and the structure matrix is the matrix of correlations between each factor score and each item. And as with the pattern matrix, we now have two columns. We'll have one column, in this case for the correlations between factor score A and each item, x1, x2, x3, and x4. And then the second column will be the column of correlations between factor score B and each item, x1, x2, x3, and x4. And these correlations will still be the same as the beta weights, even though our regression equations now contained two predictors for factor score A and factor score B. Because these two predictors, because the two factor scores are orthogonal, because they're uncorrelated with each other, the effect of one predictor by itself is the same as the effect of one predictor after controlling for the other, because they're unrelated to each other. They have a zero correlation. So that means that because the beta weight from just one predictor, the standardized beta weight, if I have a regression equation with just one predictor, the standardized beta weight will be the same thing as the correlation. If I have two predictors, and those predictors are orthogonal, then the standardized beta weights for both predictors will still be the same thing as the correlation. So our structure matrix, the matrix of correlations, is still the same thing as our pattern matrix, because our components, or our factors, are orthogonal. They're uncorrelated. And this slide is giving us SPSS output from our example, just showing that what I just said is true. So at the bottom, we have results from a regression analysis where I used factor score A and factor score B to predict item 1, X1. That was the one where people rated how much they were selfish. And we got a beta weight of 0.79 for factor score A and a standardized beta weight of 0.47 for factor score B. And at the top, I have correlations where I look at the correlation between X1 and factor score A, and that's still a correlation of 0.79. And the correlation between X1 and factor score B is a correlation of 0.47. And you see that exactly matches the standardized beta weights we got from the regression analysis. And now we're ready for the next step, which is to calculate the communality for each variable. That is, we want to calculate the R squared, the percent of variance explained in each variable when it is predicted by both factor scores, factor score A and factor score B. And as our little critter down here is saying, which I'm not sure what type of critter that is, but the critter is saying because the two components or factors are orthogonal, the communality will simply equal the sum of the two squared betas for each variable. Let's see how this works. Here is the SPSS output in which I used factor score A and factor score B to predict item 1, that one rating where people rated how selfish they were. And we just looked at this output just a moment ago where we saw the beta weight for factor score A was 0.79 and the beta weight for factor score B was 0.47. Now the communality for this particular item, for item X1, for the rating of how much people thought they were selfish, the communality is simply the R squared, the percent of variance explained, when we use both factor score A and factor score B to predict item 1. And we have that in our output up here. Here's our R squared. We explained about 85% of the variance in that item using these two factor scores or component scores. And note that we can just take this beta weight for item 1 and square it, and the beta weight for item 2 and square it. So we take 0.79 and square it, plus 0.47 and square it, gives us 0.845, which is our R squared. Normally, this doesn't work out. But because we have two orthogonal factors, it does. Because each of these beta weights, recall, is the same thing as the correlation. And if we square it, we get the percent of variance explained by each factor. And because our factors are orthogonal, they don't overlap. Normally, you just can't add up percent of variance explained for each item and get the total percent explained because the items overlap. Some of the variance explained by X1 usually is also explained by X2. So because predictor variables usually are not orthogonal, because predictor variables usually overlap with each other to some degree, you can't simply add up their squared correlations and get percent of variance explained. But in this case, we have variables that are orthogonal. They're completely unrelated, so we can take these beta weights and know that those standardized beta weights are the same things as correlations. We can square them, get the percent of variance explained by each factor, and in this case, we can simply add those squared correlations together to get the total variance explained by that item. So now we will simply do this for each item on our instrument. So we'll take item 1, question 1, and take the loading for factor score A and square it, and the loading for factor score B and square it, and add those two squared loadings together to get the communality for item 1. In other words, these two factor scores, or these two component scores, are explaining about 85% of the variance in item 1. And then we'll do the same thing for item 2. We'll take its loading on factor score A and square it, take its loading on factor score B, square it, add it together, and we get the communality for item 2. And we see we're explaining about 75% of the variance in item 2 is explained by our two components, or our two factors. And then we do the same thing for item 3, and we see that we're explaining about 63% of the variance in item 3. And we do the same thing for item 4, and we see we're explaining about 72% of the variance in item 4. So now we have created our communalities for each item on our assessment instrument based on both factor score A and factor score B. Then next, we will calculate the eigenvalues and the proportion of variance explained for each factor. So we did this previously for factor score A, and that will stay the same because all the factor loadings, or the component loadings, they will all stay the same. So the sum of the squared loadings for each factor will stay the same. But we haven't done this for factor score B yet, so now we need to do this for factor score B. So the eigenvalue, we take the sum of the squared loadings for all 4 of the loadings on factor score B and add that together, and that will give us our eigenvalue. Then we divide that by the number of variables, or the number of items on our assessment instrument, and we get the proportion of variance explained by factor score B. So here is what that looks like with our current example. Now, we already created the eigenvalue for factor score A in our previous step when we extracted only factor score A, and that is still the same here. We took each loading, we squared it, we summed all 4 of those loadings for that factor, we got an eigenvalue of 1.77, and then we divided that eigenvalue by the number of items to get the percent of variance explained in those 4 items by our eigenvalue. And we found out that factor score A explained 44.25% of the variance in those 4 items. 1.77 divided by 4 gave us 0.4425. And now we're going to do the same thing for factor score B. We'll take each of its loadings on each of these 4 items, and we'll square each of those loadings, and then we will sum those squared loadings. And in this case, the sum of those 4 squared loadings gives us 1.18. That is the eigenvalue for factor score B. And then to determine how much variance in our 4 items is being explained by factor score B, we'll take our eigenvalue and divide by 4, and we find that factor score B is explaining 29.5% of the variance in our 4 x variables. 1.18 divided by 4 gives us 0.2950. Note a couple things about what's going on here. First, note that the eigenvalue and the percent of variance explained by factor score A is larger than the eigenvalue and the percent of variance explained by factor score B, and that will always be the case. That's because our first factor was created by figuring out what loadings will maximize the amount of variance that can be explained by these loadings. And so factor score B is created by taking the residuals, all the leftovers, and trying to get beta weights, or weights for our loadings here, that will maximize the amount of variance that can be explained in those residuals, in the leftovers. So factor score A is taking the biggest slice of the pie that it can take in explaining variance in these 4 items. And factor score B is trying to explain variance in the leftovers, whatever was left over by factor score A. And so whatever factor score A did, factor score B isn't going to be able to match it. It will do something less. And so that will always be true, is that the first factor you extract will always have the highest possible eigenvalue and the highest possible percent of variance that it's explaining in your items. The next factor you extract will always have a smaller eigenvalue. It won't be able to do quite as well because it's trying to explain variance in all the leftovers. It's trying to do a more difficult task. It has all the stuff that factor score A couldn't do. Factor score B is trying to see how much it can sweep up, but it's trying to sweep up after factor score A's leftovers, and it doesn't have as much to work with. So it's going to explain less variance. Factor score B will have a smaller eigenvalue and will have a smaller percent of variance that it explains in the items. Also, note that we have one step where we calculated communalities, and this other step where we're calculating eigenvalues. And both of these involve summing squared loadings. The communality is we're going to sum across rows, and we'll create a communality for each item. So each item has a communality, and the communalities are created by summing squared loadings across rows. So we take x1, sum the factor loadings for x1 to get the communality for x1. For x2, we sum the squared factor loadings for x2 to get the communality for x2. For x3, we sum across the row to get the communality for x3. So we're summing across rows of squared factor loadings to get communalities. In contrast, for eigenvalues, we're summing down columns. We take the squared loadings for factor score A and sum them to get eigenvalue for factor score A. We sum the squared loadings for factor score B to get the eigenvalue for factor score B. So in other words, to create communalities, we sum squared loadings across rows. To get eigenvalues, we sum squared loadings down columns. And we get a separate communality for each item on our assessment instrument, and we get a separate eigenvalue for each factor score on our assessment instrument, or that we're extracting in doing factor analysis. And next, as before, we're going to reproduce the item correlation matrix. That is, we'll take that matrix algebra formula where we take our matrix of factor loadings or matrix of component loadings, like our pattern matrix, and we'll tip it on its side and multiply it by itself. Or if you want to, you can just know that we use our component loadings and plug them into this formula to produce our capital R hat, our reproduced correlation matrix. And because we now are trying to reproduce our correlation matrix not based on just one set of factor loadings, but on factor loadings for factor score A and factor score B, we're likely to do a better job of reproducing our correlation matrix. So in the bottom half of the slide, I have the results for our current example. In the middle, I have the reproduced correlation matrix based on what I get when I use both factor score A and factor score B. So I have my pattern matrix or my structure matrix, they're the same thing, the matrix of component loadings, and I plug it into the formula where I'm essentially multiplying that matrix by itself to get my reproduced correlation matrix. And the correlations I get are right here in the middle. That's my reproduced correlation matrix. And at the top, again, I have the actual correlations. That's the same as it's always been. These are the actual correlations between my four items. And then I can create my residuals, where I take each correlation from the actual correlation matrix minus the reproduced correlation matrix to get the residual. And note that I calculated these using unrounded values. Some of these don't come out quite exactly right using the rounded values I have in these tables. But if we had unrounded values, you would see these all come out just exactly right. So we take negative 0.3 minus negative 0.23, and that comes out to negative 0.07. 0.59 minus 0.78, we get negative 0.19, and so forth. So we create our residuals. And as I mentioned before, we can look at the size of these residuals to get a sense of how well a factor score or a component score is doing in explaining variance in all of our X variables, in all of the items on our questionnaire. If a factor score or a component score does a really good job of explaining variance in our items, then it will also do a really good job of reproducing the correlation matrix. If we have a factor score or a component score that does a really bad job of explaining variance in our X variables, then it will also do a really bad job of reproducing the correlation matrix. So we can look at the size of the residuals in our for our reproduced correlation matrix to get a sense of how well a factor score or a component score is doing in explaining variance in our X variables. And so I mentioned that before. One thing I didn't mention is that we can calculate something called a root mean square for our residual. We have our matrix of residuals here, and I can calculate a root mean square for that matrix to get a good sense of what the size of these residuals are. And this is kind of just a fancy way of taking an average of the absolute value of these residuals. But rather, I suppose the easiest way to do it was simply take away the negative signs and take the sum of the absolute values and then divide by the number of elements in your matrix to get the average absolute size of the residual. But instead of doing that, we're going to do something a little more fancy that will accomplish essentially the same thing. And we're going to take each of these residuals and square it. So we'll take each residual and square it, and then we'll sum all the squared residuals, and then we'll divide by the number of residuals to get the average squared residual, and then we will take the square root of the average squared residual to give us the root mean square. So the root mean square is the square root of the average of your squared residual. And in this case, our root mean square is 0.25, and we can understand that as simply the average absolute size of the residual is all that's really telling us. So on average, the average magnitude of these residuals is about 0.245. Now this top table of residuals, this is the one we saw before when I had just one component or one factor, when we had just factor score A, using that one to try to explain variance in our x variables, and before we calculated factor score B. So the top table is showing you the residuals we saw with that very first step when we had only factor score A. And now this bottom table is showing you the residuals we saw on the previous slide just a moment ago. I'm back up here. Where is that? On this slide right here, this very bottom residuals here. So this bottom table is that table of residuals we just looked at when we tried to reproduce the correlation matrix using both factor score A and factor score B. And what will always happen is that your residuals when you have just one factor or one component will be larger than the residuals when I have two or more components. So I now have both factor score A and factor score B, and my residuals went down from an average of 0.245 to an average of 0.173. So my residuals are getting smaller. In other words, my root mean square for the two component, for when I use both factor score A and factor score B to predict my x variable, my items. In that case, my root mean square is 0.173. In other words, my average residual, when I compare the actual correlation matrix to the reproduced correlation matrix, the average residual in this case is 0.173, and it was larger when I only had one factor score. And that will always be true, and we can get a sense of how well we're improving our ability to predict scores on x variables when we add factors by looking at the size of these root mean squares and seeing how much they decrease when I add another factor to try to explain variance in my x variables. Now we're going to repeat this process yet one more time. So now we're going to extract both factor score A and factor score B out of each x variable. And so then we'll have a table of residuals, and I'll standardize those residuals, and I'll then create a new factor, maybe call this factor score C, or component score C if I want to be more precise. And I will calculate a new component, a new factor, to explain variance in the residuals of my x variables, all the stuff that couldn't be explained by factor score A and factor score B. So recall that when I extracted that first factor, I created that table of residuals, all the stuff that couldn't be explained by factor score A, and then I calculated the component weights, or the factor score weights, to create factor score B, and I created those weights to explain as much as possible of the residuals, all the stuff that couldn't be explained by factor score A. So factor score B was created to explain as much as possible of the variance in the residuals of my x variables. And so then I'll extract both factor score A and factor score B out of my x variables, and I'll have a new table of residuals, this time all the stuff that couldn't be explained by either factor, and I'll create a factor score C, and I'll give the loadings for factor score C will be created to explain as much as possible of the residuals of my x variables. That is, the residuals, all the stuff that couldn't be explained by factor score A or factor score B. So we're just creating factors, then we calculate residuals, all the stuff that couldn't be explained by those factors, and then we create new factors to try to explain variance in those residuals, the leftovers, the stuff that couldn't be explained. So we'll do all those same 6 steps with factor score C. Then, as you might guess, we can do this one more time. Once we have 3 factors, factor score A, factor score B, and factor score C, or to be more precise, 3 components, we can do this a 4th time. We can extract a 4th factor, trying to explain all the variance of my x variables that couldn't be explained by factor score A or factor score B or factor score C. So we can do this 4 times. We can extract 4 factors to try to explain variance in our items on our assessment instrument. Now, I cannot keep on doing this over and over again infinitely. There is a limit to how many factors or components I can extract. Specifically, I cannot extract more components or factors than I have items or variables on my assessment instrument. So if I have an assessment instrument with just 4 questions on it, I can only extract 4 components or 4 factors, and I cannot extract any more factors than that. And once I have extracted a number of factors that is the same as the number of items on my questionnaire, or components, if the number of components or factors is equal to the number of variables or items on your questionnaire, at that point I will have explained 100% of the variance in my items. So if I have a 4-item questionnaire, if I extract 4 components or 4 factors, at that point I will have explained those four components will explain 100% of the variance in my items. And at that point, it's not mathematically possible to extract any more factors or components. So here are how things look for our current example. If I extract all 4 of the possible components from my 4-item questionnaire. My questionnaire has 4 items, 4 variables on it. So my maximum is to extract 4 components or 4 factors. And here is the pattern matrix if I extract all 4 of those components. And the pattern matrix would be identical to the structure matrix. Those 2 matrices are still the same thing. It's just that the pattern matrix is a matrix of beta weights when we use factor scores to predict items. And the structure matrix is the correlation matrix between our components or factors and items. And those are still the same thing. And in our first column, we have the factor loadings or component loadings for factor score A. And those are the same as they've always been. In our second column, we have the loadings for factor score B, and those are the same as before. And then what I've added here are the loadings for factor score C and the loadings for factor score D. So now we have factor loadings on 4 different factors, and we're using these 4 factors to try to explain variance in 4 items. And now on this slide, I've simply added the communalities and eigenvalues to our pattern matrix. So again, communalities, we take each loading and we square it, and we sum across the row to get a communality for each item. And as you can see here, all of our communalities now sum up to exactly 1, because we're explaining 100% of the variance in each item. If I try to use these 4 factor scores to explain variance in 4 items, I can perfectly explain the variance in every item. So every item will now have a communality of 1 because I'm explaining 100% of the variance in each item. And likewise, I can sum down the columns to calculate the eigenvalue for each factor or each component. So the eigenvalue for component 1 is 1.77. We saw that before. We saw previously that the eigenvalue for component 2 was 1.18. And now I'm adding the eigenvalue for component 3 is 0.76. And for component 4, or factor 4, is 0.26. Note, I mentioned before that these eigenvalues will always decrease, and see that's happening here. That our first eigenvalue is the biggest, the next one's going to be smaller, the next one's going to be smaller, and the next one's going to be smaller. Because each successive factor is trying to explain variance in the leftovers of the stuff that couldn't be explained by the factors before it. And so each successive factor is trying to explain variance in a smaller and a smaller slice of the pie. Each successive factor has less to work with, so each successive factor will have a smaller eigenvalue. And so we see that we started off with 1.7, then it dropped to 1.8, then to 0.76, and then to 0.26. One thing to note here is that the sum of my eigenvalues, if I extract all the factors that I can extract, or all the components I can extract. So if I have 4 items, I extract 4 factors or 4 components. The sum of my eigenvalues will equal the number of items that I have. So if I have 4 items, the sum of my eigenvalues will be 4, and that will always be true. So the sum of your eigenvalues will always equal the number of items that you have if you extract all possible factors or components that you can extract. And now let's take each eigenvalue, divide by number of items, divide by 4, to get the percent of variance explained by each factor. We already saw that factor score A explained 44.25% of the variance in my items, and that factor score B explained 29.5% of the variance. And now we see that factor score C explains an additional 19%, and factor score D explains 6.5%. And if we add that together, 44.25 plus 2.29, so if we add across this row, we see that altogether we explain 100% of the variance in our items. So whether we look at communalities or look at the percent of variance explained from the eigenvalues, either way we're showing that once we extract all 4 of the possible components, we're now explaining 100% of the variance in the items. And one thing, I have a note at the bottom of the page here. If you're calculating along any of these, you might know there's a few places where things don't sum up to exactly 1 or 100%. And that's because this table has rounding in it. When I sum to 100%, these sums over here are based on unrounded values. So if I use unrounded values, it comes out perfectly. If you look at the actual values in this table is rounded a little bit, and so things might not come out quite as perfectly if you use the actual values in this table. But if you use unrounded values, you can trust me, everything will come out perfect. That will be 100%. You will explain 100% there. Your commonalities will be all 1, and you will explain 100% of the variance in your 4 items using 4 factors. And let's look at what happens if we try to reproduce the correlation matrix when I'm using 4 factors or 4 components to explain variance in 4 items. What happens is that I can perfectly reproduce that correlation matrix. So in the middle again, here's that reproduced correlation matrix where I use that formula where I take my pattern matrix, my matrix of factor loadings or component loadings, and I tilt it on its side and multiply it by itself using matrix algebra to get my capital R hat, my reproduced correlation matrix. And in the middle, these are the correlations I get when I plug that formula in. When I use that formula with my pattern matrix, my table of factor loadings or component loadings to recreate the correlation matrix, I get these correlations right here in the middle of the page. And note that the correlations in the middle are identical to the correlations at the top, which is the actual set of correlations from my actual data set. I got 0.06, negative 0.3, 0.59, same exact correlations here. So what this is showing you is that when we've extracted the same number of factors or components as we have items, then when we try to reproduce our correlation matrix, we will perfectly reproduce it. And so down at the bottom, I've calculated my residuals, and all the residuals are exactly 0 because we've perfectly reproduced that correlation matrix. So at this point, you may be wondering, what was the purpose of all of that? If I have a 4-item questionnaire and I extract 4 components or 4 factors, and those 4 components explain 100% of the variance in my items, what good does that do me? What do I accomplish by doing that? Or if, say, for example, I had a 25-item questionnaire and I extracted 25 factors out of my 25-item questionnaire, and those 25 factors explained all the variance in my 25 items. What good does that do me? I've mentioned before that factor analysis is supposed to be a data reduction procedure, but if I extract 25 factors out of 25 items, I haven't reduced anything. I've just mathematically rearranged my data set. What do I accomplish by doing that? So what we're going to do is this. First, we go through a process where we extract all the possible components or factors that we can extract. We extract as many components or factors as we have items on our questionnaire. Then we go back and look at our results and we make a decision. We make a decision about how many factors or components we really needed to extract. So we decide what is the fewest possible factors that I really need to explain as much variance as I can in my items. So I want to figure out what's the smallest number of factors that I can extract that will explain a sufficient portion of variance in my items. Or another way to say the same thing, what is the smallest number of factors I can extract that will sufficiently reproduce that correlation matrix? So I want to go through a process of trying to decide what is the smallest number of factors I really need. But to make that decision, first I go through the process of extracting all the possible factors that I can extract. And once I've done that, I have a set of results that I can look at, and I can look at those results and then make a decision about what is the fewest number of factors that I really needed to extract. And so in that way, we can actually reduce the number of factors we use. Now, that process of deciding how many factors or components to extract, there's a few different ways we can do that. And as you will see, some of these approaches, in fact, all of them to some extent, involve somewhat of a subjective process. It's not a cut and dry, here's how to do it and here's the correct answer, but different researchers might use different ways of doing it and they might come to different conclusions when they do it. So this is one of those subjective points of doing factor analysis where sometimes people come to different results depending on how they choose to go about doing it. So let's look at some of those ways we could try to decide how many factors we really need to extract. So here are some of the most common ways of making a decision about how many factors we need to extract. So again, we do this process by first extracting all the possible factors or components that we can extract, extracting a number of factors or components that is equal to the number of items on our assessment instrument. And then we look at those results to make this decision about what is the fewest number of factors that we really needed. And then eventually we'll focus on a solution, a factor analysis solution, using only those factors that we needed to extract. So one way of making this decision is simply to use theoretical judgment. That is, to look at results and look at different what happens if you extract 1 factor or 2 factor or 3 factor or 4 factor, and look at your component or factor loadings and try to make a judgment about, does one solution seem more sensible or seem to make more sense than another solution? Say, for example, I was doing a study where I had people rating how much they liked different foods. And maybe I extracted a 2-factor solution and found that ratings for how much people liked bananas and apples and oranges all loaded really high on factor A. And maybe how much people liked broccoli and Brussels sprouts and carrots all really loaded high on factor B. And I would say, oh, that makes theoretical sense because it looks like factor A is capturing all how much people like fruit. And factor B tends to be capturing how much people like vegetables. And so that might make theoretical sense. And then maybe I extract 3 factors. And maybe the first factor has high loadings for how much people like bananas and how much they like Brussels sprouts. And the second factor has high loadings for how much people like apples and how much people like broccoli. Those 2 items load really high on my second factor. And maybe how much people like oranges and how much they like carrots have high loadings on my third factor. And I would look at that and say, that doesn't make a whole lot of theoretical sense. I don't really understand what these factors are indicating. They don't really make sense because we've got bananas and Brussels sprouts on one and apples and broccoli on the other, and that just doesn't make theoretical sense. So in this case, I might say, well, the 2-factor solution seemed to make more theoretical sense than the 3-factor solution, so I might just go with that. Or another thing we could do, and this is actually if you use SPSS to do factor analysis and don't put any defaults into it, if you just go by the defaults that it gives you, SPSS will automatically do this for you. But one thing we can do is say, well, let's extract as many factors as have eigenvalues greater than 1. Recall that if you extract a number of factors or components that is equal to the number of items you have, then the sum of all your eigenvalues will equal the number of items. Another way of thinking about the same thing means that if your eigenvalue is greater than 1, it means that that factor or component is explaining more variance than an average single item. If an eigenvalue for a factor or component is less than 1, it means that that factor or component is explaining less variance than a single item would. So this idea is that once you extract factors that are explaining less variance than a single item, those factors or components are no longer useful. And so the logic goes, we should extract as many factors or components as have eigenvalues greater than 1. And once we've extracted that number, once we start extracting factors that have eigenvalues less than 1, we should stop. So only take factors or components that have eigenvalues greater than 1 and not ones that have eigenvalues less than 1. So that's another way. Another way is we could do something called using a scree plot. And a fourth way is to do something called a parallel analysis. And I'm going to illustrate both a scree plot and a parallel analysis on the next slides here. So first, here is a scree plot. So this is another way of trying to decide how many factors to extract. And a scree plot is simply a plot of your eigenvalues for each successive factor. So this example right here is actually from a factor analysis or a principal component analysis, actually, where I had 12 items on a questionnaire. And so what this is showing is that the eigenvalue for my first variable, my first item, was right here, right, a little bit above 3. The eigenvalue for my second item was right here, a little bit above 2.5. The eigenvalue for my third variable was right here. And the eigenvalue for my fourth variable or fourth item was a little bit above 0.5. And for my fifth was about the same, and sixth, they're going down kind of slightly here. So this is just showing you the eigenvalue for each successive component or factor that you extract. The eigenvalues are on the y-axis, and each successive component or factor is on the x-axis. And so what we're looking for here is there a break in this line? The term scree plot, the word scree, I believe, refers to the rubble that would lie at the bottom of a cliff. So if you have a cliff, and at the bottom of that cliff there's a whole bunch of rubble, I think sometimes the rubble at the bottom of a cliff is described as scree. And the idea is that when you plot this, you should have an idea of here's a cliff, and then here's a drop off, and here's all the rubble lying at the bottom of your cliff. So you're looking at a picture that looks like a cliff with a drop off with a bunch of rubble at the bottom of it. And that is why this picture is sometimes called a scree plot. And The idea, if you're going to use a scree plot to decide how many factors to extract, is to look for where that cliff occurs and to extract all the factors that are on top of that cliff and to reject all the factors that are in the scree. So in this picture right here, all of these factors down here would be in the scree, and we've got a big drop-off right here, and we've got 3 factors at the top. So this would give us a visual illustration suggesting that maybe we should extract 3 factors and no more. Now note this is a rather subjective opinion here, because trying to look at a picture and decide where is the drop-off can be a rather subjective judgment. Now, I've picked an example here from a study that actually has a fairly clear-looking drop-off. Usually it's going to look a little more ambiguous than this, and it's harder to decide. When I was a graduate student and took a course in factor analysis, I recall my professor for that class gave a suggestion about how to interpret a scree plot. What he said is that you should take a pencil and lay a pencil over this bottom line here. I'm going to take a pencil, I'm going to try to make a little point there. Here's my pencil. And you lay it over there, and he suggested that anything that the pencil covers up is a factor you should reject, and anything that goes above the pencil is a factor that you should keep, which that illustrates in part how subjective this decision can be. And of course, that would make a difference about how thick your pencil is and how big your plot is. But that's a general idea. We're trying to find that point. Where is there a drop-off in your eigenvalues, where you're extracting factors, and that one has a big eigenvalue, and that one has a big eigenvalue, and that one has a big eigenvalue, and then suddenly you have a factor that drops off and has a really tiny eigenvalue, and that's the point where you stop extracting factors. Note, by the way, in this case, if we use that rule of extract as many factors as have eigenvalues greater than 1, we would actually extract 3 factors as well. So here is eigenvalue of 1. If we just draw a line right here, note that we actually have these 3 factors up here, or components, all have eigenvalues greater than 1, and all the others have eigenvalues less than 1. Things often don't come out quite as neat as this, but this is a nice, neat example that if you follow either rule, either way, if you extract factors that have eigenvalues greater than 1, you'd extract these 3 factors. Or if you use a scree plot, it looks like we have the drop-off here that would also suggest extracting only 3 factors. So that is how you use a scree plot. So a 4th method we can use for trying to decide how many factors to extract is to do something called a parallel analysis. And with a parallel analysis, what we're going to do is try to imagine what the scree plot would look like if we really didn't have any factors at all and everything was just random chance findings. And we're going to create this parallel scree plot based on this idea of everything is just random chance findings and there's no real factors at all. And then we're only going to extract factors if their eigenvalues exceed what we would expect based on the parallel analysis of what we would get if there was just random chance findings. So here's what we're going to do. We'll ask the computer to simulate a population where all items have correlations of 0, where there's 0 correlations. In other words, if none of the items are correlated with each other, there are essentially no factors. Nothing's actually related to each other. It's just no factors. All the items have 0 correlations with each other. So the computer will simulate a population where I have a set of items where that's true. And the computer is then going to draw a sample of cases from that population that will have the same sample size as what I'm using in my study, and will have the same number of items as on the assessment instrument that I'm working with. So if I had a sample of 20 people and they took a 4-item questionnaire, the computer would create this sample with 20 people and 4 items. And it would draw that sample from a population that it created, where in the population, all the items have correlations of 0. None of the items are correlated with each other. And then the computer will conduct an exploratory factor analysis on that simulated sample that it created and calculate the scree plot. It will calculate the eigenvalue for each factor. And then it will repeatedly draw from that population and create new samples And each new sample, it'll calculate an exploratory factor analysis on that new sample. And each time it does it, it's going to get a slightly different set of results because it's drawing different samples from this population. Now in the population, all the items have a correlation of 0. But when it draws a sample, sometimes the items might have positive or slightly negative correlations. It's not going to be exactly 0 in each sample. And each time it does an exploratory factor analysis, it's going to come up with slightly different results. And so the computer will replicate this over and over several times. And then it will create the average eigenvalue. That is, it'll create a scree plot giving the eigenvalue for factor 1, for factor 2, for factor 3, however many factors it extracted. It will extract as many factors as there are items on the assessment instrument. So if we have an assessment instrument with 4 items, it will extract 4 factors in each analysis. And it will compute the average eigenvalue each of those times. And then we'll have 2 scree plots. We'll have the scree plot from the parallel analysis using the average eigenvalue for each factor, and the actual scree plot from our analysis from our actual study with our real eigenvalues. And our plan will be to keep each factor if its eigenvalue exceeds the parallel analysis averaged eigenvalue. So this is what a parallel analysis looks like. Here's an example. I used R to do this example. And in your projects, you will do a similar example and get output that looks kind of like this as well. So we see the blue line, this line right here, is a scree plot for the actual study that I did. So in this study, I had a 12-item questionnaire, and we see the eigenvalue for my first factor or first component was above 5. The eigenvalue for my second one was a little bit above 2. And my eigenvalue for my third one was a little bit below 1. This particular plot has drawn a line, right, equal to an eigenvalue of 1. So if you want to use that rule of accepting components or factors that have eigenvalues greater than 1, you can just pick the ones that have eigenvalues above that line right there. That's why they put that line there for you. And we see we have 2 components or 2 factors that have eigenvalues greater than 1. And then what we have here is this dotted red line. And that dotted red line is from the simulated data set from the parallel analysis. That is, when the computer simulated a population where all the items had correlations of 0 with each other, and then drew samples from that population that had the exact same sample size as what I used in my study that produced this blue line here. So it had the exact same sample size as what I had in my study, and it drew items to have the exact same number of items as I used in my actual study, except for the simulation was drawing from a population where all the items had correlations of 0 with each other. So technically there were not any factors in that population because everything's correlated 0 and it's not possible to have any factors. So the red line here is giving us the average eigenvalue. So if it extracts the average eigenvalue for the first factor or first component was a little bit above 1. The one for the second was right here, and right about when I get to about the 6th component, it's right about at 1, then it starts dropping below 1 for the 8th, 9th, and 10th, and so forth. So the red line is showing us the results from the parallel analysis from the simulated data set where it's drawing from a population where there's really no factors, and so these are the eigenvalues you would expect to get just by chance alone. So the blue line is showing the eigenvalues that I actually got in my study, and the dotted red line is showing the eigenvalues that you would get just by chance alone in a situation where there's actually no factors at all, but you have the same number of items and the same number of people in your data set. What would you get just by chance alone? And so we see that factor number 1 has an eigenvalue that's greater than that dotted red line. It's an eigenvalue that's higher than what we would expect if we were just getting results based on chance alone. The second factor also has an eigenvalue that's greater than that dotted red line, but the third factor falls below that line. And again, I've given you another example that's nice and neat and clean because If we extract a number of factors that have eigenvalues greater than 1, we'd extract these first two factors. If we follow the rules of the parallel analysis and extract factors that have eigenvalues greater than the average value from our parallel analysis, that is, eigenvalues that are higher than this dotted red line, we would also still extract two factors. Although in this case, I suppose if we use our scree plot, it's not quite as neat. We still can say, I suppose, if we use that pencil rule, if you were to put a pencil over these, you would still have two factors sticking up above that pencil. But this drop off, we have a kind of a big drop off from factor 1 to factor 2, a much smaller one here. And so if you're using that rule of just looking at the scree plot and trying to decide where is the big drop off, I could imagine one person saying, well, I think the big drop off is right here. We should only extract one factor. And another person saying, well, I think the drop off is right here after the second factor, so we'd extract the first two. So there's a place where subjective judgment might lead to different decisions about how many factors to extract. But if we follow the rule of extracting factors that have eigenvalues greater than 1, or the rule of using the parallel analysis and extracting factors that have eigenvalues greater than the parallel analysis estimate of what the eigenvalues would be from a random data set, both of those processes would lead to the same decision of extracting two factors in this example. And now we're ready for the next topic, which is to talk about rotation. But maybe I will pause here and put rotation on our next video.